Hi, my name is Lam Kakin, student ID EEE 2409079. So for this project, we have used copper wires enameled to avoid short circuiting the whole thing. And then for the LEDs, we're using the red ones, which are rated at 1.2 volts, which is easier to power up with a spin from your human hands. And then for the magnets, we're using neodymium magnets. We're using about 8 of them. And we have pieced them together on both sides of the chopsticks. And we have used 2 pieces of chopsticks to avoid the magnets collapsing on each other. I'll pass it on to the next guy.
Hello, Sir Kuzairi. My name is Eugene Raul Kurnia, and my student ID is EEE2409098. And today I'm gonna explain to you how electricity, voltage, and or electricity are produced. According to the Faraday's law, this is the Faraday's law. Voltage or EMF, electromagnetic force, is produced through the change of magnetic flux. And from that Faraday's law, we get this formula. You see here? The most important thing when doing this is you need to know how to turn the magnets. If you're turning the magnets in the same direction as how the coil are turns, you're gonna get a 0 degree. And degrees are really important in this formula because you see here, the theta here shows the degree difference between the magnetic flux, between the magnets and the coil turns. So if you spin the magnet in the same direction of the coil, you're gonna get a 0 degree, which means you're not gonna produce any voltage. Well, if you do it in a perpendicular way or you get a 90 degree, you're gonna get a max voltage or EMF. That's why it's really important for you to arrange how the magnet turns from a 0 degree or 90 degree. You need to know this.
My name is Sim Aaron Fabrian. My student ID is EEE 2409101. I'll be demonstrating this magnet coil and the voltage that it produces with the LED. I don't know if you can see, but every half turn, the LED turns on, and then for the other half turn, it's off. This is because for one half turn, it corresponds to the positive voltage of the sine wave, and the other half turn goes to the negative side of the sine wave. When it's positive, it powers the LED because the LED only turns on when it's forward biased. During the negative part of the sine wave, it turns off because it's reverse biased. This LED is roughly 2 volts, so the amount I'm generating with my fingers should be around that area. I'll turn off the lights so you can see better. This is the negative half turn, this is the positive turn, negative, and then positive, negative, and then positive. And if I use my secret technique, I'll be able to power on the lights of the class.
Hi, my name is Xu Zhengwei, student ID EE2409072. So I'm going to demonstrate you guys voltage and current and resistance. All right, turn this thing on.
Move it.
All right, it's on voltage right now, and it's in voltage DC. All right, as you can see, if I turn this thing, about 0.2 to 0.3 volts. But if I change it to AC, that's voltage. If I go back to DC, there's like a positive and negative and positive, negative. All right, to the current. AC current. Yeah, about 10 milliohms, 10 milliampere for the AC. And yeah, positive, negative, positive, negative. And our total resistance for the whole coil, it's 24.3 ohms.
Hi, I'm Shazir Rizwan, student ID EEE 2409100, and today I will be talking about the way we can improve our project. So, to improve this design, we could add more powerful neodymium magnets, increase the number of coils for a stronger output, or make the rotation smoother using a bearing or motor. Even adding a rectifier could help us convert the AC to DC for practical usage.